Good morning, class. Absolute 5 here. So, today we're going to talk about a very interesting theorem. What theorem is that? Well, the theorem is, it's called either the sandwich theorem or the squeeze theorem. Preferably, I prefer the squeeze theorem because I don't want to think of sandwiches, but however you like to think of it, it's a theory that you're able to squish another function between two other functions, so you force the function for it to go to 0. So let's write that out. What is the squeeze theorem? What does it say? It states if the limit as x approaches a for f of x is less than or equal to the limit as x approaches a for g of x, and that's also less than or equal to the limit as x approaches a for h of x, when x is near a except possibly at a, and that the limit as x approaches a for f of x is equal to the limit as x approaches a to h of x is equal to L, then the limit as x approaches a for g of x equals L. Okay, so now what does this mean? This is a lot of stuff I wrote. So what this is saying is that this is the physical part where it's, you see there's a function here, there's another function here, and then there's another function there. They're all taking the limit at the same points. So what this is saying is that when x is getting really close to a but not exactly a, then that means that the limit for this, for f of x and h of x, they have to equal L. But since these two conform to L, that means it must be true that g of x conforms to L. Almost like peer pressure. If you think about it that way. Think of it that way, that if two of your friends like PlayStation, then you're bound to like PlayStation eventually because your two friends like PlayStation. That's just an example. Or Xbox or Nintendo, whichever one you prefer, or I don't know, like politics or whatever. The point that I'm saying is that you notice that's the idea for the example. So let's have a physical example of what it is that we're actually talking about. And the best example that pretty sure everyone knows, not everyone knows, but at some point they've seen this example where you must show that the limit as x approaches 0 for x squared sine of 1 over x must equal 0. So immediately, here's the thing. When you see the word show that means you're proving that this limit exists at 0. That's what this whole argument is saying, that you're going to prove that this function goes to 0. So the first thing that a lot of people would assume is, oh, Roger, couldn't you just take the limit as x squared times the limit as x approaches 0 for sine of 1 over x, and then that would equal 0? And the answer to that question is no, because the thing is, you get undefined here with 1 over x, and not only that, this would be 0, so you have 0 for 0 situation, which really you wouldn't be able to do anything with that situation anyway. So this is a big no. You cannot just decide to use the property multiplication to just show this and that. So let's think, what can we do then? So the main problem isn't the x squared, it's the sine. So let's take that sine, right? Sine over 1 over x, right? And let's remember, what's the range? So we know the domain for sine is infinitely going to the right and going to the left. But what about the range? How far does it go up? Between 1 and minus 1, because is periodic. It's like the serpent. It keeps going from 1 to -1 all the time. So we're going to use the less than and equal to signs they're kind of like boundaries. So this way, well, the sign function, it bounds itself by default, so that because it does that, it automatically has to, this is why the range for this is why we're using 1 and -1, because the sign goes from 1 to -1, if you know the range for this. Now, for this to look like this function, we have to now use, let's multiply everything here by x squared. So we're given -x squared is less than or equal to x squared sine 1 over x less than or equal to x squared. So now if we take the limit, now here's the part. So pretend this is our f of x, this bottom one is our g of x, and this one to the right is our h of x. So based on the theory is that if we can show that the limit for this is 0 and that the limit for 8, so if we show f of x and h of x goes to 0, then by default g of x has to go to 0 based on the squeeze theorem. So let's show that. If we take the limit as x approaches 0 for a -x squared, right? So if we take the limit of this, well, we know this is just going to be 0x squared, which is just 0. We know that's true. And if we take the limit as x approaches 0 for x squared, well, we also know that that's also 0. So then, based on the squeeze theorem, hence, therefore, that these three dots mean therefore, that because our f of x and h of x are equal to 0, that's basically your L, that's your output. Since they both go to 0, then it's true that the limit as x approaches 0 for x squared sine of 1 over x has to go to 0. And that's how you show the proof that based on the squeeze theorem that the function has to go to 0. Let me just get a marker real quick because I want to show it visually so you guys get a better understanding of what it is to show that this is that. So I'll keep the question there. So ideally this is what you want to see on the graph. Visually it looks like this. Okay, so the triangle there, arrow I mean. Okay, so we have this. Alright, so this is -1, and this is 1. 5, 1, 2, 3, 4, 5, doesn't matter. It's here that matters. So we have -x squared. So this opens down. That's a down parabola. So our f of x down here is -x squared. This is -x squared. And then you have h of x, which is just a regular parabola. It opens up. Now, this one, your g of x is your sine of 1 over x. So, well, technically it's your g of x is x squared sine. So this function here, right? You're going to notice that it's going to oscillate like this, but then it's going to get smaller and 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 smaller to the point that it's forced to go to 0. No matter what happens here, it can't, because remember, the range for this, it goes off like this. That's why if you notice that the sign has to eventually commit to going to 0 based on what this graph looks like. So that's why the squeeze theorem, that's why you see how these two parabolas, they're sandwiching the sine function by default. So they're kind of like compressing it, they're forcing it to go to 0 whether it likes it or not. So that's what the squeeze theorem does, is that it forces another function to go to another function. So that's the squeeze theorem for you guys. I hope you liked this video. Be sure to like, share, and subscribe to this channel. Be sure to also hit that bell button if you want more notifications from my channel. And I believe this is a pretty well-known theory that's actually really proven to be very simple, and it's very easy to understand. And that's basically it for the lesson. So this has been Absolute 5 from Roger Palomino. And math is infinite because there are infinitely many possibilities. So have you guys an absolutely lovely day.